Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we talk about all things Gen Chem related. On this video, I'll be covering orbitals and the quantum numbers associated with them. Let's get started. The amount of energy associated with an electron and the position in which it's located are complementary. And for every electron, we can define the amount of energy based on the position in which it's found within the atom. Now, that region in which the electrons are found is what we call our orbital. And so the orbital really is just a probability distribution map of a region where the electron is most likely found. Now, there's a large series of equations that have been studied and looked at to death, but that's a little bit outside of the scope of this class. So what we're going to look at is the end result, using the information from all these studies that have been done to be able to predict the location of where these electrons are. Now, the big thing that we need to remember is that a lot of the properties that we know about atoms are based on where these electrons are found within an atom. So there have been a lot of calculations done that help us to understand the size, the shape, and the orientation in space of any orbital that we're going to be looking at. And it's really based on identifying these three integer terms that are found within this wave function. Now, these three terms that we're going to be defining are what we call our quantum numbers associated with the positioning of an orbital. There's going to be three main quantum numbers that we're responsible for. And in chapter 8, we're going to learn about a fourth one that's going to help us to really predict and understand where every electron in any atom is located. The three quantum numbers that you're going to be responsible for are your principal quantum number, which gets a symbol of N, your angular momentum quantum number, which gets the symbol of L, and the magnetic quantum number, which gets a symbol of ML. Now, each one of these are going to tell us different pieces of where that electron is located. Our principal quantum number is going to talk about and help us figure out the distance from the nucleus, which energy level is it found on. The angular momentum quantum number is going to help us to determine the shape, what kind of orbital is it in. And the magnetic quantum number is going to help us to understand the orientation in space. So let's first focus on our principal quantum number, or the N quantum number. Now, the N quantum number is going to characterize the energy of the electron in a particular orbital. So again, each energy level found outside of the nucleus would have a corresponding N value. Now, the further away you get from the nucleus, the higher and higher that N value will go. N must be an integer greater or equal to the number 1. So closest to the nucleus would be N is equal to 1. Then N is equal to 2, N is equal to 3, and N is equal to 4. And the higher and higher we go in that N value, the more energy that the orbital will have. Now, energies are typically defined as being negative. And remember, when we are having that transition from a higher to a lower, we'll be releasing energy in that form of light. The larger the value of N, the larger the possible orbitals can be within that particular orbital. And it's also important to note that as you go higher and higher, the amount of energy between each orbital is going to get smaller. And you can actually calculate the energy associated with an electron using the equation that's found below. Now, the shape of our atomic orbitals is based off of that. The shape of the atomic orbitals is based off of that L quantum number. So the L quantum number is primarily used to determine the shape. And this can have any integer value from 0 up to N-1. And so typically when you're doing these assignment of these quantum numbers, you're doing it in series. You first need to think about, well, what is my N value? And then you can predict the possible L values based off of that N value. And again, L can be any integer value up from 0 up to N-1. So again, if N is equal to 1, that means that my L values can be 0, only 0, because N-1 is 0. If N is equal to 2, then my possible L values could be 0, 1, and that's it. If N is equal to 3, the possible L values are 0, 1, or 2. And when N is equal to 4, your possible L values can equal to 0, 1, 2, or 3. And so you may be asking yourself, well, what does this mean? How do I relate this to understanding what an orbital looks like or where it's found? Well, each of these L values, 0, 1, 2, or 3, correspond to a specific type of orbital. When L is equal to 0, those are your s orbitals. Okay, so that means in the first energy level, we have s orbitals present and only s orbitals present. For your L is equal to 1, those are your p orbitals. And you can notice that means that in our second energy level, we have s's and p's present. When L is equal to 2, those are your d orbitals. And so that means in the third energy level, we have s's, p's, and d's. And when n is equal to, when L is equal to 3, those are your f orbitals. And that means in the fourth energy level, we have all of the different types of orbitals found. Now, each of these orbitals do have their own characteristic shapes and relative sizes. Your s orbitals are your smallest orbitals, and I'll show you pictures in a second, but these are often found as more spherical shaped, okay? Your p orbitals, those tend to look like 2 balloons tied together, so a little bit bigger. Your d orbitals look like 4 balloons tied together, so even bigger. And your f orbitals look like 8 balloons tied together. So these are our biggest orbitals found. Like so. A great way to think about this whenever you're trying to put this in perspective, I love to think about this in terms of like a housing plan. And so your n orbital, your n quantum number helps you to understand the street that these orbitals are found on. So n is equal to 1 means that you're on the first street close to the nucleus. N is equal to 2, you're on the second street or second energy level. N is equal to 3, third energy level, so forth. Now, each of these represent the types of houses that these electrons could be found in. So an s orbital, those are your smallest houses. So it's like a studio apartment. Your p orbitals, those are your second smallest. So those are more like a townhouse. The d orbitals, now you're getting a little bit bigger. That's what those 4 balloons, that's like a single family home. And then the f orbitals, those are our largest. And so that's kind of like a mansion. And so on one of these streets, on one of these energy levels, you can have a variety of different types of energy level or orbitals that can exist. And again, we're tying this back to our n quantum number, which is telling us our street or energy level, and the L quantum number, which is telling us the shape of that particular orbital. So the s orbital is shown for you here. Again, you can see that nice spherical shape. It is the lowest energy orbital in a principal energy state or within an energy level. And so compared to your p orbitals, d orbitals, or f orbitals, the energy associated with this is the lowest. All right, and so then as you get higher and higher in your n value, you go up the streets. The actual size of the s orbital gets a little bit bigger, and all the orbitals get bigger as you go higher. But again, compared to their counterparts, your p's, your d's, or f's, s orbitals are the lowest energy orbitals that exist. Now your p orbitals, again, that's when you're dealing with L values of 1. Your p orbitals can be actually found in 3 different orientations. And this actually leads to our third quantum number, which is our ML value. So that ML value that you can associate or assign to anything, your ML value is equal to negative L values up to positive L values. And you would list these as integers. Okay, and so whatever L you define, so let's say we're saying L is equal to 1, well, that means my ML values could be -1, 0, and +1. Now notice we wrote down 3 numbers there. So the fact that we came up with 3 numbers for our ML value tell us that there are 3 different orientations for how these p orbitals can exist. And that's going to be in our x-axis, the y-axis, or the z-axis. Okay, so our ML value, that's the one that's going to tell us the orientation. Or if you like that housing example that I gave to you, it's like the address of that particular house. Because, you know, you could have several houses that look very similar, but each one has their own individual address or own individual orientation where they're located on a street. And so comparatively, these are our second lowest energy orbitals within a principal energy state, and they tend to be 2-lobed or look like they have 2 balloons that are tied together. Okay. And so you can see here pictures of the 3 different p orbitals. Again, those 3 would coincide with that -1, 0, +1 value that we assign from our ML values. Now our d orbitals, those coincide with an L value equal to 2. And so if you have an L value equal to 2, that means our ML value, remember, which can be -L up to +L, would have 5 values. It would be -2, -1, 0, +1, and +2. The fact that we wrote 5 numbers down, -2, -1, 0, +1, and +2, coincide with the fact that there are 5 different orientations for these orbitals, okay? And so I'll show you pictures in a second, but you can see compared to our p orbitals or our s orbitals, these ones are much bigger. Remember, these are a single family home, so they're higher in energy compared to your s's or your p's. Or remember, if you think about, I talked about it a few videos ago, think of energy like money. So the money needed to get these huge orbitals, the energy needed is much greater. Okay, and so you can see pictures of all 5 of our d orbitals found for you here. And so again, you could assign them as -2, -1, 0, +1, +2. And then last but not least, an L value equal to 3, those are our f orbitals. So f orbitals, again, those are our largest orbitals. They look like 8 balloons tied together. And if we look at our ML values for that L value equal to 3, we would say that ML values are -3, -2, -1, 0, +1, +2, or +3. And so since we wrote down 7 numbers, that tells us that we have 7 different types of F orbitals that can exist, 7 different orientations. And a lot of these do tend to be 8 load. We do have some ones that have some little funky shapes to them, but overall they're much bigger, much higher in energy than our S's, our P's, or our D's. And so you can see here in this picture, we have 7 different orientations that exist for these F orbitals. So now when we put all this together, our N value, our L value, our ML value, this is what's needed to really describe an orbital. Where is it located and what kind of orbital are we dealing with? So each set of N, L, and ML value describes one orbital. And we're going to learn in chapter 8, one other quantum number that we're going to add that's going to talk about the position of the electrons within the orbitals. So orbitals that have the same N value are on the same principal energy level. They're on the same street. Orbitals with the same N and L value are considered to create what's called a sublevel or a subshell within that energy level. And so you can see here a breakdown of different energy shells and subshells that exist within our different principal energy levels. So again, look at N equals to 1. So again, N equals to 1, that's where we're closest to our nucleus. So N is equal to 1. That means my possible L value is just 0. And my possible ML value is just 0. I only wrote one number. So one number tells me there's one type of S orbital that exists in that first energy level. And that S would create the S subshell. In the second energy level, N is equal to 2. So again, because N is equal to 2, our L values could be 0 or 1. Which tells us I have S or P orbitals that exist. Now, if we look at the ML values for each of those L values, when L is equal to 0, the ML value is also equal to 0. One number tells us one type of S orbital exists. And for our L equals to 1, our ML value would be -1, 0, or +1. 3 numbers tells us 3 different P orbitals exist. So notice within the second energy level, we have 2 different subshells that exist, an S subshell and a P subshell. In our third energy level, we have N is equal to 3. So our L values could be 0, 1, or 2. And then we would have the subsequent ML values based off of each of those L values. So when L is equal to 0, we have an ML value of 0 as well, one number, one type of S orbital. When L is equal to 1, the ML values are -1, 0, +1. 3 values means 3 different P orbitals in that subshell. And when L is equal to 2, our ML value is -2, -1, 0, 1, or +2. And 5 numbers means 5 different types of d orbitals. So again, in our third energy level, there are 3 subshells. So the energy level, that number, also tells you how many subshells you could expect to be found there. So putting all this together, we now want to try to predict what are the quantum numbers and the names associated with an orbital found in the n is equal to 4 principal level, and how many orbitals actually exist. So we are going to have to go through the progression. We start by looking at what our n value is. We then assign the possible L values, and then can assign the ML values. So it's a stepwise process. So when n is equal to 4, we know that our L values, we could have several of them. Our L values could be 0, 1, 2, or 3. Remember, you assign L values by listing any integer value from 0 up to n-1. Each one of those numbers that we write for the L value have a specific orbital or type of orbital associated with it. Our L value of 0, that's for our s orbitals. An L value of 1 is for our p orbitals. An L value of 2 is our d orbitals. And an L value of 3 is our f orbitals. Now, we know what kinds of orbitals there are. So we know when we're doing the naming of them, this would mean that we have 4s, a 4s orbital, at least some 4s orbitals present. We have some 4p orbitals present. We have 4ds, and we have 4fs. Now, it's important to note that when I'm saying 4s or 4p or 4d or 4f, that's not saying I have 4 of each of those. That's just basically defining what street is it on, what energy level is on, and what kind of orbital do we have. It's not telling me the number of them. That number comes from our ML value. You have to do an ML value for each of the L values that you have. Remember, your ML value is equal to -L up to +L. So when L is equal to 0, your ML value would only be 0. And so that tells me we have one type of s orbital present. When L is equal to 1, the ML value based off of 1 would be -1, 0, +1. That means we have 3 types of p orbitals that exist, 3 different orientations. When ML is equal to when L is equal to 2, our ML values are -2, -1, 0, +1, and +2. So that tells me we got 5 types of Ds, and ML value based off of L being equal to 3 would be -3, -2, -1, 0, +1, +2, or +3. And so what that tells us is that we have 7 types of f orbitals present. So to figure out the total number of orbitals that exist, we would have to add all of those up. So 1 + 3 + 5 + 7 is going to give us a total of 16 different orbitals. Okay, total. And so we have addressed the 2 questions here. Something quick I do want to show you that if you are trying to figure out how many orbitals exist in any principal level, you could also just take n squared, and that's going to tell you the number of orbitals present in that energy level. So if you look at 4 squared would give us 16, and that coincides with the value that we see based off of going through all the calculations. Now, where we're going with this, in chapter 8, we're going to be learning and building out electron configurations. And with those electron configurations, specifically with the orbital diagrams, we're going to be able to look at an electron, where it's positioned in the orbital diagram, and assign an N, an L, an ML value, and this 4th quantum number, which is called an MS, or the magnetic spin quantum number, to every electron that's in there. So one thing you want to remember is that The first number, when we're writing down an orbital name, that tells us our N value. And the letter that's found here is going to coincide with whatever L value we have. Our ML values are going to be related to the orbital position that the electron is found in. And we'll get into that in subsequent videos. I hope this video helped you understand our 4 quantum numbers associated with defining an orbital. Make sure you guys like, comment, and subscribe, and let me know what other content you would like to see. I'll be back with some more videos later. Have a great day. Talk to you guys soon. Bye-bye.